Okay, so we've talked about how to create an interval, but a lot of times the sample size is chosen before the interval is done, before the study is done, based on the margin of error they want. So what sample size will we need in a follow-up study if we wanted a margin of error of 5% with 98% confidence? And we're talking about what's on the previous slide, which was the experiment that had a 27% and the n was 53. We had a margin of error of like 15 on that, which is pretty large. So how many people would you need in the study if you wanted to lower that to 5% and you wanted to be more confident, you wanted to be 98% confident? So the z star for 98% is 2.326. That's one of the three I asked you to memorize. 90%, 1.645. 95% was 1.96. 98% was 2.326. And 99% was 2.576. Okay, but you should have these memorized. I will not be giving you a table with this data on it for the quiz. Okay, and I think I planned the quiz for what, Wednesday or Thursday? Okay, Wednesday or Thursday, probably Wednesday. And the quiz will just be one problem. One problem. You have to check the conditions, create the interval, interpret the interval, and then there'll be a follow-up. I guess there's two questions. A follow-up question where you have to calculate n like this. Okay. So the margin of error is the part of our interval calculation that's z star times the standard error, which is p hat q hat over n. Now, a lot of times we don't know what p hat's going to be when we want to decide what our margin of error is or what our sample size should be. So when you're not given a p hat to use, you estimate with 0.5. 0.5 is going to give you the largest sample size that will give you a margin of error of whatever you asked for at that confidence level, because 0.5 times 0.5 is the largest your p hat q hat can be. So in this case, though, we did an initial study and we got a p hat of 0.27. Assuming that it's going to be the same in this follow-up study, how many people do we need to have in our experiment to have a margin of error of 5%? How do I make 5% a decimal? 0.05. Okay, don't mess that part up. 0.05. And that's going to equal my z star for 98%, 2.326, times the square root of 0.27, 0.73 over n. And now we use our algebra skills to solve for n. It's been a while since we've used algebra skills. So we're going to do what first? Let's divide by 2.326. This was Chapter 5, Algebra 2. How do you solve an equation that has a square root in it? I'm doing it right now. 0.05 divided by 2.326, 0.0215 equals the square root of, what's 0.27 times 0.73? That's 0.1971 over n. I just multiplied the 0.27 times the 0.73. So to undo the square root, we square both sides. So we get 4.63 times 10 to the negative 4 equals 0.1972 divided by n, 71 divided by n. Leave it in your calculator. Don't round it yet. And then we get multiply by n So we have to times both sides by n to get it out of the denominator. And then divide by 4.36 times 10 to the negative 4. This is just a little bit of algebra. You don't even have to do the math part in your head. You just have to use the calculator. So I'm going to do 0.1971 divided by second answer. I'm going to leave the unrounded numbers in my calculator until the very, very end. Of course, I'm going to round on my paper, but I'm going to use unrounded numbers until the very end. And I get 425.45. Can I have 0.45 people in my sample? No. So we're going to round up. So 426. You get marked off if you don't round up. Yes? I divided, or I squared 0.0215. Get rid of the square root. Oh, I just messed up I inverted my numbers. But my answers are correct. Why? Because I left the numbers in my calculator. So this is what it looks like in my calculator. So that's how I did it in my calculator. How did I get this? What the heck? This is a totally separate example. What sample size does it take to estimate the outcome of an election with a margin of 3%? Correct. For this one, we have no prior knowledge about what we think P might be or P hat. So we're going to use P hat equals 0.5. 50% is the largest P times Q can be, 0.5 times 0.5. If I lower P or raise P, that number gets smaller than 0.25. So the highest that can be is when I use 0.5. So it's going to give us the largest number that's going to give us our margin of error. And it's okay if our margin of error is smaller because it means we're more accurate, right? But we don't want our margin of error to be bigger. So we use 0.05 when P is not given. Okay. Same formula. 95% is going to be 1.96. We're going to use 95% because almost all polls about elections or anything like that is done with a 95% confidence level, and 3% margin of error. So what's 3% as a decimal? 0.03. So equals 1.96 times the square root of 0.5 times 0.5 over n. If you want to do 0.5 times 0.5 first, 0.03 equals 1.96, square root of 0.25 over n. So we're going to divide by 1.96. We get 0.01531 equals the square root of 0.25 over n. And we're going to square both sides to undo the square root. So I'm going to hit square in my calculator. I get 2.343 times 10 to the negative 4. equals 0.25 over n. And then n is equal to 0.25 divided by 2.343 times 10 to the negative 4. Times by n divided by the coefficient. Times by n. We got 2.343 times 10 to the negative 4, n equals 0.25. And then divide by the 2.343 times 10 to the negative 4. And so 0.25 divided by my answer in my calculator is 1067.1. So 1068. It doesn't matter how small that decimal is. It could be 0.0001 and you are still going to round up. Okay. So in order to estimate the outcome of an election with a 3% margin of error and 95% confidence, they need 1,068 people in their survey. Yes?
If we use 0.5 for Q, why wouldn't we use 0.95 for Q?
Because 0.5 plus 0.5 is 1. We're not using 0.05, right? We're using 0.5, 50%. Yeah. Right, and that's why it's so important to make sure you do those decimals correctly. P hat will be 0.5, but margin of error should be always have a 0 in front of it. We don't usually want a margin of error of 10%. So your margin of error should always have a leading 0 decimal. Okay? Here is an AP exam question. This is question number 1 from 2002. In 1915, Einstein's theory predicted that the curvature of space denoted by gamma was 1, while Newtonian theory predicted it was 0. Since 1915, scientists have repeatedly found estimates of gamma using various methods and procedures. Each estimate has a margin of error. The figure below displays the estimate plus or minus the margin of error. So when we look at this, see if I can get this working. There we go. The point in the middle, the dot in the middle, is the estimate, and then the sides are the margin of error. So they believe it's between here and here. Here, 21 experiments done over time. Okay? This is the earliest experiment to the most recent experiment. Okay? Where are the questions? So here are the questions based on the display on page 6. This was on a separate page. Describe how the precision of the estimates of gamma has changed over time. What can you say about the precision of the estimates over time based on this graph? They've gotten more accurate, right? The smaller the interval, yeah, the gamma is that Y-looking thing. As the interval gets smaller over time, that means they're getting more accurate, right? So it's getting more precise over time because the intervals are getting smaller. B says, write a few sentences describing the strength of evidence the experiments possible provide for the claim from Newtonian theory that gamma is equal to 0. Your response must include justification based on the display. What would you say our display says about the theory that gamma is equal to 0? It's not likely at all. Not one of the intervals has 0 in it. Right? So over time, and we've gotten more and more precise in accurately estimating gamma, but there is no evidence that gamma is equal to 0 because none of our intervals capture 0. And then write a few sentences describing the strength of evidence the experiments provide for the claim from Einstein's theory that gamma equals 1. What do we think? Yeah, almost all of the intervals. Do some of the intervals miss the mark? Yeah, right? Some of them miss the mark. 1, 2, 4 of the intervals actually miss the estimate, 4 out of the 21, right? So there's strong evidence that gamma equals 1 because only 4 out of the 21 experiments didn't include 1 as a possible estimate in their interval, right? And as time went on, the actual estimate gets even closer to 1 with very little margin of error. Okay, so that's an example of number 1 on the AP exam is like your, let's get you into this, you know, we're going to give you an easy question. It's usually not requiring a lot of calculations. It's interpreting a graph. And so that's usually how the AP exam starts.